Good morning, good afternoon, good evening, wherever you may be in this part of the world. Welcome to another session of my presentation series. And this time, the topic is electrical power generation utilizing hydro energy. I've made a series of presentation of different sources of energy to produce electrical power. And the first one is pump storage energy, and also producing electrical power from fossil fuel, and that is gas and coal. And this time, it's electrical power generation utilizing hydro energy. My good name is John Kweku Amotu, and I've been an electrical engineer for the past 31 years, and I'm based in the United States of America. I've been practicing for the past 31 years. Okay, so now let's talk about some logistics here and what you need to do. Okay, so this is my YouTube channel. The name is Work and Happenings, talking to the engineer, and this has a lot of presentation material over there, and basically you can go there and basically watch numerous presentations out there as a young engineer, right? As a developing engineer, as an experienced engineer, as a mid-career engineer, and as a consulting engineer. Okay, so for you to be able to subscribe to my channel, right, this is the subscribe button. You need a Google account. Okay, so you can create a Google Gmail, and that should give you the ability to be able to subscribe to this channel, and for that matter, any other channel. If you like my presentation, don't forget to select the like button. And also, don't forget to share this knowledge. Very, very important. Okay, so I made mention about this logistics here and what you need to do. Okay, so for you to be able to subscribe to my channel, this is my YouTube channel and has a lot of presentation material, technical material for the power systems engineer. So for you to be able to subscribe it, you need a Google account. Okay, Google Gmail. Okay, and this is the subscribe button. And if you like my presentation, select the like button, and don't forget to share that knowledge. Okay, so now let's take a deep look at the schematic of hydropower plant and basically walk through all the processes that are involved, that are integrated to the whole hydro power plant to generate electrical energy from a renewable energy source, that is water, and that's hydro. Okay, so behind this dam, right? This is a dam, right? And usually a dam is built utilizing heavy concrete. Heavy concrete. You're talking about 60 stories building, right? And basically, heavy concrete is utilized to, basically achieve this dam and create a reservoir. So that reservoir has a lot of, energy, potential energy, right? And based on the height, volume of water that is basically kept behind this dam, right? So this is a heavy wall, and it stretches miles. I would say about, half a mile to a mile, depending on the size of the hydro power plants. Right? Okay, so if you're able to achieve that, it means that you are blocking the flow of the river. And some of the dams or the reservoirs are man-made. And I think the one in Ghana, if I remember, it was basically it's man-made from Lake Water, right? Okay, so and others to achieved, from different sources. Like it can be basically the flow of a large river, and basically they block the flow and divert the river to basically flow in a different direction, right? So that they can achieve this reservoir capacity. So think about it. This reservoir, when it is created, also stretches miles. And think about it: 6 stories building for a large size of dam, just like the Three Gorges dam in China, right? Okay. So now, how do we get the water to flow from the reservoir or the dammed lake or river, right? Okay, so this is through this channel over here called a Penstock, and we'll see a picture of how the Penstock basically, look like. Remember, I made mention that the pictures are always worth more than 1,000 words. So this is just a 2D, picture, and 2D to 3D, picture of how it looks like. But actually, I'll show you the real picture of how the Penstock looks like. Okay, so before this gate, there's a gate over here, right, called Sluice gate, Sluice, and that is the intake, right, intake point of the hydrodam, right? Okay, hydro generation plant. Okay, so for you to basically make it possible for the water to flow from this dam, right, you need to open the sluice gates, right, and various control schemes are put into place, and now that we are in basically, AI world, much more enhanced technology world, so basically a lot of this opening and closing is achieved, can be achieved remotely or local, right? Okay, formally, in those days, a lot of this opening and closing is done right at the forefront of the sluice gate itself, right? Okay, so once you open the sluice gate, what are you trying to achieve? That force of energy, that amount, enormous energy, flows down this piping, right, to the turbine. So this is the turbine part, right, of the hydro generator, and this is the generator itself, right? And in between the generator and the turbine, you have a shaft that joins both. So hydro generators are vertically mounted, right, because of the nature of the way the energy source flows in towards the turbine. So it has to be vertically mounted. Most of them, I'm yet to see one that has horizontal mounted generator. Maybe, some coupling can be put into place, where basically you can have a turbine that is integrated to another turbine that is horizontally mounted, so that, you create just like a gear system, then you can achieve a horizontal mounted generator, but I'm yet to see that. Okay, so at the output of the generator, then goes to the rest of the world, right? That's your transmission. Okay, so this is basically the Three Gorges Dam in China, and that is one of the largest dams in the world, right? Okay, so remember I made mention that a heavy concrete, right? This is the heavy part of the concrete, and beyond this is the dam and reservoir, right? Okay, so this concrete, remember I made mention that the concrete is about 60 stories building, very heavy concrete, right? And remember, for them to basically, what they do is basically they divert the river to flow in another direction, right? So formerly the river used to flow in this direction, right? Then they divert the river to flow in another direction, where then after that basically they're able to achieve a land where it is dry for them to build this dam. After that, then they divert part of the river towards the side. Okay, so the river can flow to that part that they diverted. Then another part can come to the side to create the volume of reservoir that is needed. Okay, so this is also another picture of another dam, and like I told you that this is how so you can see that this is a typical river that flows through all these gorges, and basically this heavy concrete, right, very deep down, is built. to be able to achieve this volume of energy over here, right? So that has a lot of potential energy, and when it is released towards the turbine, that is what flows through the penstocks to be able to turn the turbine. And once you're able to turn the turbine, and you consequently turn the generator, because they are all coupled to the same shaft, right? Okay, so the heavy water that you're seeing here, let me explain to you, sometimes, with time, there's a lot of sediments that build up behind this dam, right? Okay, so when these sediments build up periodically, what it is if an action is not implemented to mitigate or remove these sediments, what will happen? You basically end up limiting or reducing the size, the volume of water. Hence, the amount of water that you need to generate electrical power wouldn't be enough, right? Okay, so what they do is periodically they flush the sediments out, utilizing these big time faster sluice gates that are located on top here. So instead of the water going through the turbine, they divert it to another gate where basically it basically flushes, all the sediments that are located behind the dam. Next is another beautiful picture of a typical dam and reservoir, right? Okay, so that is your reservoir that is created, and this is the whole dam. So I'll say that this one is like half a mile to 1 mile length, right? And heavy concrete. So this is a picture of how they flush the sediments. Remember, I made mention in the last 2 slides how they flush the sediments out of the dam, the reservoir, right? Okay, so they flush it. You have sluice gates. Basically, instead of the water going through the turbine, it goes through another gate to flush out because this water has a lot of sediments, and you don't want that water going through the turbine, because what it is you end up destroying and eroding the turbine blade. So it goes through another part and basically flushes out a lot of the sediments that have been built behind the dam. Next is another picture of flushing out the sediments from a different angle. Another beautiful picture of how this water, after it goes through the turbine, basically the afterflow. So they call this part afterflow, right? Afterflow, right? And in certain configurations, right? In addition to the hydro dam, this water that is located in the afterflow can be pumped back into a pump storage scheme. Right? And what is the pump storage, right? Remember, I've made a video presentation on the pump storage, right? A pump storage is achieved when you have let's say, a very tall hill, mountain, then basically this mountain, is dug out, and basically concrete and other things are installed, right? Then water is filled with water, right, to create a reservoir. Right, and you have piping that comes down that also turns other turbines and generator to generate water, hydro turbine generator, right? Okay, so these are mostly used for peak shavers, right? Emergency demand of electric power, right? So you can have that closed loop and basically configuration where basically you don't allow the afterflow just to go to waste, so you basically pump it back to a pump storage system to basically get the required electric power when you need it during peak time. Next is remember I think the first 2 or 3 slides I made mention of when I was describing the schematic or the components that are integrated to hydro power plant, right? I made mention of the penstock in the sluice gate. Okay, this is a picture of the penstock, so you can see the huge piping. So this is what the water that is gushing out from the reservoir. You have a reservoir here with water. This is where the water flows, and this is the gate valve, right? This is the sluice gate, right? And basically I think it's hydraulically controlled, open and close, right? So it allows the water to basically flow at a faster rate and with a lot of energy, right? Potential energy, right? To mechanical energy and electrical energy, right? Comes out. Okay, so now let's talk about the location of the hydro generators, right? The bay that all these generators are located. Okay, so for this particular dam, I think the Gorges hydro dam, we have 24 generators, right? So that's how large this generator is, and I think each one is about 700 megawatts. So that's a large power plant, right? Okay, so they are basically lined, like this in bays, and they are vertically mounted. Remember, I made mention that you have the turbine here, right, with the impellers, right, and you have the Penstock, right, with the gushing water that's from the reservoir, right. So, and basically it turns this turbine. This turbine is connected to the generator through a shaft, right, and it comes out to electrical power, then it goes to a step-up transformer to the outside wall. So this is basically a lineup of how the generators are mounted. And like I said, they are all vertically mounted. So pictures are worth more than 1,000 words. And basically, remember I mentioned that the turbine right here, they are connected with a shaft. And this is the generator, right? So this is the rotor of the generator. That is how the shaft of in between the turbine, this is the turbine, are integrated together. Okay, so this is basically the shaft, how it looks like, and as you can see, vertically mounted. So now let's talk about how hydro generators are built, right? And it's so beautiful, how these are built. Okay, so as you can see over here, right, these are cores. This is the core part of the stator, right? So they are building the stator, right? And to build the stator, you have to build the magnetic. This core is basically the magnetic part. That is what helps to build the magnetic field, right? So that induction can take place. Okay, so because without a magnetic field, there's no way you will have induction or voltage into the stator core, right? Okay, so this is the building block of, and these are laminations that are stuck together. As you can see, they are stuck all the way up, all the way up, all the way up. Now, okay, and these are the laminations, and these holes you see over here, they call them through bolts, right? So bolting basically goes through it to basically keep it all together. Building bolts or through bolts, whatever technology. It's I think GE calls it through bolts, and I think Siemens calls it building bolts, right? Okay, but they all mean the same thing, right? Okay, so heavy, basically big time bolts go through these, just two, and the bolts are insulated. Okay, because remember, the goal is to prevent circulating currents due to eddy currents, right? So these bolting that basically keeps these laminations together has to be insulated. Okay, so this is basically the frame of the stator. So this is the stator, right? The generator has two components, the stator and a rotor, right? So this is the stator, right? The stator is the stationary part, and like I told you that the building block of the stator is the core, right? You are building the magnetic path, right? Okay, so this is what they are doing, right? All around the circumference, right, of the core, right? And basically, inside the core, they have basically path, or basically throws that allows the coils to be inserted. And you see a picture of it. Okay, so these are the coils, right? These are the coils that have been inserted inside these throws that you see inside, the coils, right? Okay, so they come, it's called rubel shape, right? Okay, so the coil shape, it's called rubel. So they basically go there, they go through this path in the coil, and basically this is the end winding. This is where the end winding is basically prepped up, so. And basically, the three-phase is achieved at the end winding area. So a group of coils is all tied together in phase A, and another group of coil phase B, and another group of coil phase C. Right? So this is how they are connected. They say pictures are worth more than 1,000 words. So this is basically the coil throws, that I was talking about. This is where the coil go through, right? Okay, so you can have a top coil and bottom coil, right? Depending on the size of the generator, right? Okay, so the coil comes here, and basically these are all the basically, the end. They call them, they are mechanical components basically that keeps the core in place, right? Okay, so as you can see, it has a bolting in place, right? And this is basically the coils coming out, and basically groups of coils are basically connected together to create a phase A, phase B, phase C. Right. So this is the core of the generator, right? Okay. So remember I made mention that they have bolts that go through it horizontally, and also they have bolts that are insulated that go through it vertically. The goal is basically to have a mechanical, robust, clamping for this core, because of the enormous electrodynamic forces that the generator is goes through during operation, and matter of fact during fault conditions. I mean, think about it. It's I squared, right? The fault current, right? The dynamics of the forces, right? This force is equal to I squared T. So that's a lot of current, and fault current squared, right? And times I squared times D being the area where the fault is located. Okay, so that is why a lot of mechanical bracing is put into place too, so that the generator can withstand all these electrodynamic forces when it is in operations due to high fault currents, right? Okay. So now let's talk about the end here, right? You can see that the end is in the form of a step ladder, right? Okay. So this is done basically. It's a graded form, because the flux, flows, and this is an exit, right? So you want it to be graded. Other than that, you get a lot of heating here, right? So that is why we have this step ladder, and also at the same time it helps the faster flow of the flux, and gives the flux an easier path of flow. Okay, so now let's take a look at this beautiful picture. Remember, I made mention that the coils go through the core, right? It goes through the core. So this is the core, right? And this part is the exit part, right? So the exit part, this is how the cores are basically prepped, right? They are braced together. Remember that, because of the electrodynamic forces, that goes into place during steady state operation of a generator and during fault condition, right? So these coils are braced together, right? You have lashing tapes, they call them lashing tapes, right? That basically hold these coils together, and basically epoxy is added to even make it much harder, right? So these are, one that you see over here, they call them lashing tapes, right? And epoxy is added to it so that it makes it basically very solid and keeps it into place, right? Okay, and also, after the coils are inserted, basically, it is dipped in epoxy to make it much more hardened, and basically gives it much more mechanical bracing and endurance. Okay, so much talking about the stator of the generator. Now let's move on to the rotor part, right? The generator, remember I made mention that has two components, the stator plus the rotor, right? And the previous slide we talked about the stator, right? The stator is the stationary part, and the rotor is the rotating part, right? Okay, so for hydro generators, right, it is a salient pole, right? Rotor. It has a salient pole rotor. And what does the salient pole rotor mean? These are the poles, right? These are the poles, and the poles are the ones that has the rotor winding on it, right? A salient, a hydro generator, has a lot of poles, right? So that is why it moves at a slower speed. So think about it. A typical generator has about 100 of these, right? Poles, right? So what is the revolution per minute, right? Over pole pairs, right? That is 120 times 60 over 100, right? So that is about 72, right? RPM, right? So that's how slow of a speed the generator will turn, right? Compared to a cylindrical rotor that basically has only 4 pole pairs, right? Okay, so if it has a 2, that is pole pair, right? For cylindrical rotor, and that is what they use for a lot of these steam turbines, right? Okay, 120 times 60 over 2, right? If it has 2 poles, right, that is 3600 RPM, right? And if it has 4 pole pairs, right, that is 120 times 60 over 4, right? And that is what 1800 RPM, right? So compare 1800 RPM, 3600 RPM with 72. So you see why the rotors of hydro generators, turn at a slower speed, because it has many non-poles, right? Okay, so this is all basically the mechanical building block for the salient pole of these rotors. So this is a picture of the generator with the rotor part and the stator part, everything intact, and how it looks like. And this is a picture of the mechanical part, right? Okay, so these are the turbine blades of the generator, right? Okay, so these are the blades, and basically the water coming from the dam through the penstock, rushing down, basically impinges upon these blades, and basically it rotates it, right? And as it rotates it, it turns the shaft, right? The shaft is connected to the rotor shaft of the generator. So this is the turbine, right? Being basically inserted down here, and I told you that they are vertically mounted. Okay, so this is a beautiful picture of the stator, right, of a hydro generator, right? Okay, so as you can see, the end winding is basically prepared, and this ring you see over here is basically what basically produces the different phases, right? Okay, so they call it end ring. Actually, the name they call it end ring, right? So basically, groups of coils are all tied together, and basically through connected to this end ring, and to form phase A, phase B, phase C, before it comes out of the terminal box. Okay, so this is the rotor, right? And these are the poles, right? Mounted. Remember, I showed you a picture of the poles, right? And so this is a typical rotor of the generator, right? So these are the poles, right? So this is what creates your magnetic field, right? So these windings are fed with DC current from the extension system, right? Right. So once the extension system feeds it with a DC current, it builds a revolving magnetic field, right? So as it picks up speed, basically the magnetic field also starts building up. Then, because of this magnetic field, basically gets because the stator has the coils, right? The stator also has coils, and because of the magnetic path that basically the coil creates, right? induction is achieved and voltage is induced into the coil that are embedded in the stator windings. So this is the formation of the end winding, as you can see over here, right? So another beautiful picture with everything inserted, right? The rotor inserted. This is the rotor, this is the stator, and everything inserted, you know, and the turbine is all the way. The turbine is all the way to the bottom, right? Okay. Okay, so with that comes to the end of my presentation, and thank you so much for your listening. Yes, and don't forget to subscribe to my channel, and this is the subscribe button. Before you can subscribe, remember I told you you need a Google account, right? Google email. And if you like my presentation, select the like button, and don't forget to share the knowledge. With that comes to the end of my presentation, and I thank you so much, and look forward for more presentations and more beautiful presentations. And my good name is John Quickwa, and thank you again.